So the last time we had a video lecture, I was saying that all these equations that we learned about were based on one assumption when it comes to these solutions, and that is that the solutes do not dissociate when they dissolve in water. So we're talking about solutes which are largely covalent, such as sucrose, glucose, methylene glycol, and so on. Things are a bit different, however, if the solute dissociates, as in the case of ionic compounds. Now, we know that any ionic compound that dissolves in water undergoes complete dissociation. So if you have a solution that is 0.1 m, as in molality, NaCl in water, then that dissociates to form two ions, sodium and chloride ions, and their concentrations would be the same. So therefore, the total concentration of ions in this solution would be twice the concentration of the original ionic solution, right? So let's just remind ourselves that colligative properties are those properties of a solution that do not depend on the nature of the solute particles, but do depend on the nature of the number of solute particles. So in the case of the sodium chloride solution, it dissociates to form a total of 0.2 m ions in solution from a 0.1 m sodium chloride solution. And this leads us to the concept of what is known as the Van 't Hoff factor. And the Van 't Hoff factor is basically a ratio between the actual number of particles in the solution after the dissociation and the original number of formula units that was dissolved in the solution. So in the case of sodium chloride, the Van 't Hoff factor would be 2. But before we get to that, let's talk about non-electrolytes. Obviously, since non-electrolytes do not dissolve or do not dissociate in water, then the actual number of particles would be the same as the number of formula units. So therefore, its Van 't Hoff factor would be 1. Sodium chloride, as I said before, its Van 't Hoff factor would be 2. And calcium chloride, because it dissociates to form 3 ions, its Van 't Hoff factor would be 3. All right? So you have to take into account when you're looking at solving problems involving solutions of ionic compounds, you have to take into account the Van 't Hoff factor when you're doing, certain calculations. So that results in modifications of the equations that we just learned. If you're doing calculations involving boiling point elevation, then you have to include the Van 't Hoff factor here. So in other words, you have to figure out how many ions are being dissociated for every formula unit. The same is true for the equation where you have freezing point depression. And let me just mention, and I just recognize it here, there should be a negative sign here. So please make a note of that. There should be a negative sign in front of the Van 't Hoff factor in this equation. And the same is true for the osmotic pressure. Pi is equal to I, the Van 't Hoff factor, times MRT. So you have to take those Van 't Hoff factors into account when you're doing calculations regarding electrolytic solutions. And you can actually experimentally measure the Van 't Hoff factor. And what you'll find is that for the most part, there's some close correlation between the measured value and what you'd expect to get, all right? And that is seen in the table that is shown here below. So as in the case of sucrose, the measured Van 't Hoff factor is 1.0, as to be expected. In the case of hydrochloric acid, the measured Van 't Hoff factor is 1.9, which is very close to 2.0. In the case of sodium chloride, same sort of correlation, 1.9 to 2.0. Magnesium sulfate is a bit of a deviation, I should say, from this pattern. As you can see, the measured value is 1.3, and here you see that the calculated value is 2.0. And I believe the reason for that has to do with the fact that you have relatively high charges associated with the ions. In this case, you have a +2 charge here for the magnesium and a -2 charge here for the sulfate. So I think that would have some effect. I'm not sure exactly how, but I think that would have some effect on the measured Van 't Hoff factor. In the case of magnesium chloride, its measured value is 2.7, which is relatively close to the 3.0 that is expected. And then finally, in the case of iron 3 chloride, its value is 3.4, the measured value, which is a bit of a deviation not very close to the calculated value. Again, I think the same reason can be used to explain that the fact that you have a relatively high charge on the iron ion. All right. Okay. So that's basically what you have to do when it comes to ionic solutions or electrolytic solutions. You have to take into account the Van 't Hoff factor when you're doing these calculations. Okay, that's basically it for this chapter. I won't be discussing things like colloids and so on. I would instead direct you to read up on um, colloids and all the remaining topics in this chapter. All right. Okay, so the next chapter we'll be dealing with kinetics. So until next time.